So, hi, good evening, all. Welcome to that week 11 open session of PDSA course. Possibly, maybe, we are almost end of this week and the next week. We are going to end term of this particular PDSA course. Maybe you will face the examination on that 21st of this month. I think that's the thing, actually, the pattern of it. I hope you enjoyed this course. But actually, this week 11, when we talk about the week 11, Uh, as a PDSA course, we can say that it does not contain any kind of practical implementation of algorithms. It contains some kind of advanced topic which might be used when you will enter into the degree level. You will have advanced algo courses there. There you require this particular week 11 concepts what you are learning. So yeah, I think let's jump to the week 11. I think so. Shall I move to the session? Is it okay? Uh, can I jump into that? Yeah, correct. Yeah, cool. So I'm sharing my screen. Yes. So yeah, this is actually you know one summarized thing. So which it's available to quick walkthrough of the week 11. Remember, so this week 11 uh, basically it does not contain that any standard algorithms. Just it's a having a theoretical, or you can say that some kind of mathematical models we build it. That's it. So this is advanced concepts of algorithms, right? Advanced concepts, right? Maybe whenever you enter into the degree level, this particular week 11 concept, it will start there as a advanced algo beginning week. That is a kind of sequence you can find it there, right? So let's move on to that more. You can say that here there is no kind of practical implementation of algorithms. Only the mathematical model we'll walk through and we'll understand what really it is there. But this session is going to be very interesting how we are solving using mathematical models and all. Yeah. Uh, this is basically, this particular week 11, basically it goes to the various kind of parts. The first one is that linear programming model. Next, we move to that network flows, something like that. Then we have a reductions. These are all different kind of concepts. But basically, first concept is that linear programming model. So remember, earlier algorithm so far you learned so far. Maybe you work at the shortest part algorithms of Dijkstra's and Dalman-Ford in the week number 5, and Prims and Krishkal for MCST, minimum cost spanning trees. And in the week 8, you might have been went through that divide and conquer policies, where the main problem is divided into sub problems. That we have done it is divide and conquer. And then we have some kind of dynamic programming approach where you are using memoization and tabulation. Why do you use all these are for getting that optimized solution? So optimized means whether you target for a maximum value or you're targeting for a minimum value. That's called, optimized value. So optimized means maybe you'll try for maximum profit. Maybe you try for a minimum loss, something like that. These algorithms are pretty clear, and we have done some kind of practical implementation also using any kind of programming language. That's basically we know about it. But what about the linear programming? So the linear programming is simply we design a mathematical model, but outcome of this particular linear programming model is, again, our objective is to achieve that either maximum or minimum, the optimized value of maximum, or we'll try for optimized value of minimum. But remember, it is building a mathematical model only, not a straightforward algorithm. So simply we are making it as a mathematical model. So that's called a linear programming. So remember, when you develop a mathematical model for any kind of real-time scenarios, basically even in the props video lectures, you has went through that various problems, but that problems we'll discuss here also. So here, whenever you build a problem, whenever you build a solution for a problem, that problem does not contain any standard algorithms, then we will go in the way of the mathematical models. The mathematical models simply what it contains is constraints are used and objects are to be achieved. We are making some kind of constraints. Using that constraints, we try to achieve a particular object. That is what basically the linear programming it looks like. We can say that a linear function. So let us consider a linear function. Maybe it could be that f of x or something, where you have set of variables multiplied by set of constants. We have a constants are there, we have variables are there. But variables are not multiplied each other. So remember, because we have some kind of real-time scenario, if you investigate, definitely some constraints are defined. So using that constraints limitation only, we try to achieve that objective. What is the objective? Simply, it could be a maximum value or a minimum value. So this one we do using that linear programming. So remember, it does not have any standard algorithms. I think you understood what really the linear programming is. Is it clear? Is it clear? Yes. Now, let us go for some kind of example constraints. If you could look at here, see, look at here. There is a1x1 plus a2x2, where you are calling it as x is called as constants. As they said, every time constraint when you are defining, there must be some constants are there. We try to multiply variable with constant. So in this particular constraints, whatever constraints are defined, if all the constraints are there, what do you try to achieve is the k value. Similar way, b1 x1 plus b2 x2, here also x is called as constant. So the at most we are trying to optimize the value of L. So let us consider less than or equal to k means maybe you are trying for minimum value. Could call it, minimum loss. So less than or equal to k. So we are trying for greater than or equal to L means maybe you are trying for maximum. So this is what you call, maximum profit. Maybe you can call like this. This way we are trying to figure out the constraints. So using these constraints, we try to achieve our maximum objective. This particular objective, what it contains is C1, X1, C2, X2. So, and keep on going. So this way we try to achieve this objective. Maybe objective, if you could see that there is a sweet shop is there.
Sir, sorry for interrupting over here. Maximum and minimum should be opposite, I guess. Like K should be maximum and L should be minimum.
No, at most and at least, right? Can you
Yeah,
consider in that way?
at least would be L, right?
At least is would be this one, right? At least
Yes, sir.
means you are able to bear, you are able to bear, you are able to accept. Sorry, what you can say, this is not bear because it's a profit I'm talking about, right? At least L and above profit you are expecting. Is it okay? Can you consider?
Then that would be minimum profit only, right, sir? Like minimum you have to reach that profit. Above is infinity. Maximum
Maybe,
would
maybe,
be
maybe. Yeah, yeah. You are right. You are right. Correct, correct, correct. Yes, correct. You are right. Correct. Yeah, this is maximum. Correct. You are right. Correct. This is maximum. Correct. So you are able to go at most only this one, right? Correct. This is at most. Perfect. Yeah. Thank you. Correct. That makes sense. Yeah. This way we are trying to achieve that optimized value. Either it is could be maximum or minimum. So we are trying to achieve it. So remember, once again, I'm telling you, some kind of realistic scenarios, they does not have any standard algorithms. We try to build only a mathematical model. The model, it contains that constraints. And the constraints is computational. What it contains is we are trying to create a linear function with collection of variables and constants. So we try to multiply each other and then we try to achieve that the particular object. So that way we are trying to figure out. So here the complexity doesn't make a matter. Remember once again, we are not worrying about that whether it is going to be that n factorial or exponential. We don't worry about that. We will worry about that whether you are able to solve the problem or not using a mathematical model. That's it. So,
Sir, small over here confirmation. So after working out all algorithms, like none of the algorithms would fit in this problem. So we
correct,
chose to go some like off standard, like humanly,
correct,
like trial
correct,
and error method, some
correct,
sort of,
correct, correct.
which we call it,
Try and error method.
we are calling mathematical model.
Correct,
Am I right,
correct,
sir?
correct, correct,
Okay.
correct. So here, maybe you can have this problem. The Professor Mathan has discussed it. Just again, we are walking through the problem again. So remember, there is a sweet shop. Grandos sweet shop is there. Here, two products are there. They are trying to manufacture. So one is halwa and next one is burpees. So, and whenever they are making that, there are some kind of constraints are defined. So the burpees and this particular halwa, they have a profit of this burpees. One box of burpees, if you sold out, if you sell it, you will get 100 rupees. Halwa is 600. Similar lines, there is a maximum demand is there. So it does not mean that 600 halwa boxes, 600 rupees we are getting for one halwa box. It does not mean that I try to produce that as many as number of halwa boxes by ignoring only burpees. So every product has a demand. More than that, we cannot produce it. If you produce it, that's going to be loss for it because it is going to be stored. We cannot store it. It means that. That is the sense of it. Now, there is a daily demand. More than the demand, we never try to take risk to manufacture or to produce. And one more constraint is there. There is a capacity. So whatever that capacity of resources, maybe labor or whatever material you have, all these are maximum production capacity per day is only 400 boxes. That 400 boxes with combination of any of these products, either burfi or halwa. So here, what is the most profitable combination? Which combination? How many boxes if you produce of this particular halwa with combination of burfis will get you the maximum profit? So we need to figure out. So this is the question. I think you got the question, right? You got the question.
Yes, sir.
There are set of products are there, but every product is that having a maximum limit of the demand. And similar way, the inner capacity of the production limit is that only based on the existing resources is there. That is called 400. So this particular real-time scenario, we need to figure out the constraints first. So first we are making a constraints. This is what the constraints. Where the B is there, the demand is there, which is the burpees, 200. We should not exceed it. That's one constraint. And similar lines, we should not exceed 300 demand of that halwas. And combination of this burfi and halwa should not exceed that 400. That's because production limit is that. And there are some implicit constraints out there. We never go with the negative. Either 0 boxes is okay. So less than 0, it's not possible. So that this is the implicit constraint. What they are calling is, it's not defined in the problem statement, but implicitly it is involved. We never have a negative value. That's make sure one kind of constraint which is implicitly available. Our objective is you can take any combination of this burfi and halwa with this particular 100 rupees of profit and 600 rupees of profit. How much quantity of burfi boxes you will take, how much quantity of halwa boxes if you produce, we will achieve the maximum one. So this is the objective we need to achieve it. So we try for a maximum, or we can say that optimize it maximum. So this one does not have any standard algorithm. Only thing is a linear function they are making. You can see this, only the linear approach. What they have done is, so toward that x-axis and y-axis, towards that x-axis, they are taking it is burpees. Towards that y-axis, they are taking is halwas, right? This way. Maybe incrementally they are going. Incrementally means maybe they'll fix this particular 100, which is going to the burpee. And with combination of this particular 100 and 100 combination, they are trying to identify one particular vertex where the intersection of 100 boxes of halwa and 100 boxes of this burpees. And similar way, there is another intersection you can find it.
So the point C, points is determining here the point 100 point of burfis and 600 point of halwas intersection point.
No. Wait. So here we are trying to identify the intersection points which are called vertices, right? These are called vertices, which I am giving a different color. So let us this is a green color. Is it okay?
Yeah, okay.
So in this way, if you go, I can take this particular one, 200, and then 100 is there. So if 100 boxes of this burfi and 200 boxes of this particular halwa towards it, burfi and these two combination, right? This one.
Yeah.
Okay. Is it a profitable combination? We'll check it. Similar lines, they went that various combinations. Is it right?
Yes, sir.
Okay. So in the linear approach, what you can say that linear programming model, I can use it. It's another different color, right? Is it right?
Yes, sir.
So what they are doing is, in a linear way, when they are going, if this particular vertex and this particular vertex is there, whenever other nearby vertex is giving a better value, we will ignore this earlier vertex, right? Is it right?
Yes, sir. We'll ignore.
Because 100 boxes of burfi and 100 boxes of this, you will get 100 into 100 and 600 into 100. Is it right? This particular profit, what you will get? 100 into 100 plus 600 into 100, right? Is it right?
Yes, sir.
So in this way, if you go in this way, this particular one, whenever you are going is, if it is 200 boxes of burfis and 100 boxes of halwas, so what you are getting, this point is, so we are going with this way, right? This way. When you are going in this way, so what is that? So we are getting computed value?
200 into B.
Yes. 200 into B.
And 100 times H.
Yes. 100 times H. 600 into. I'm sorry. Maybe they are using this one is this is 100 actually. Maybe I don't say this one. Oh, wait. Let me erase this because I have to reflect the values, right? This is okay. My pen. Yeah. So here, so I'm using is that 100 into 200, right? Because 100 rupees is the profit, plus 600 into how much? 100, right?
100.
Hello.
100.
Hello.
100. Hello.
Hello. Can you hear me?
Yes, I
yes,
can.
Yeah. It's a profit. So the quantity of halwas is going to be. So is it a better value than this one? Is it a better value or not? This one is a better value.
Yeah, of course.
So that's the thing. We ignore this vertex and we go this way. Similar way, we go for next vertex. We go in. So in this way, if you are going, definitely the particular solution is exponential one. Is it right? Is it exponential solution or not?
Yes, sir, absolutely.
Correct. So in this way, if you are figuring out, the final optimized value is this. So when you compare this one. So in this way, linear approach, when you are finding it, maybe the solution, it goes to that exponential one. We don't mind because we don't have that either any kind of complexity constraints here because it's a real-time scenario. We are trying to figure out in this way only. So using a mathematical model, and we are trying to build the solution in a linear approach by comparing that each particular combination of two particular products. So hope you got it, right? Is it clear? Hello? Hello?
Yes, sir. Yes.
Yes, sir. Yes.
This is okay. But what happens is, whenever this particular linear programming is, okay, just let me go back. What is the summary is there? Yeah, this is what I talked manually, start with any vertex and evaluate the object. Maybe your intersection, you are choosing 100 combination, or you might choose in that 200 and 100 combination, you might choose in it. If adjacent vertex is better, move to that vertex, then we are trying to move to that vertex only, because so whatever the current vertex is there, next vertex is there, the next vertex you are getting a better value than this one, so we move to that value. So here, if no other adjacent vertex is having better value, simply we fix that current one only. But definitely here the solution is exponential solution. So we don't have that any kind of, at least of the 10 square solution also. Definitely it's going to be that exponential one. Maybe it is 2 to the power of n. N is nothing but that number of products we need to compare, because right now products are 2. Maybe we have to go in that way only. Yes. Now, example is somewhat extended. So it's the same sweet shop only, extended with some more extension. What is some more extension? What they did is, interesting thing here is, there is another product is been added, rasmalai. This is the product it was added, and daily demand was added. Maybe the daily demand for rasmalai is unlimited. So unlimited and 1300 rupees is a profit. Can we directly produce that? Whatever the maximum capacity, 400 boxes, I can produce all rasmalai? Of course we can do, but there is another constraint was given. 600 boxes of halwa or 200 boxes of rasmalai only, the milk supply is there. There is another product was added. There is another constraint also added. So what exactly it means that one box of rasmalai milk quantity, whatever the milk is there, milk constraint is there, to produce that one box of that particular rasmalai, which it requires that, which is equal to that 3 boxes of halwa. See, that's what I said. See, look at that. So 200 box of 600 box of halwa we can have a supply, or 200 boxes of rasmalai. So what quantity it is using is one box of rasmalai you want to build means 3 times of that halwas we can make it. Hope you understand, right? Is it clear? Hello?
Yeah.
Yes, sir.
So that's what 3 times. So that rasmalai requires that 3 times as much of halwa. So that it does not mean that a new product is introduced, we don't go. Because of there is another constraint was introduced, so it is going to be. Here what happened is, earlier we have seen that only x-axis and y-axis products. Now we have a z-axis also, third dimension. So whenever third dimension is there, the particular solution, we can say that more than that exponential. See, look at here. This is what constraints what they define. So the burfis, which has that, halwas, it has that, and then so whatever this particular daily demand is there, burfis and halwas and this particular rasmalai, daily demand is 400 only, because maybe not daily demand, I think yeah, capacity, I'm sorry.
Production.
Yeah, sorry, it is not daily demand, it's a production capacity. Maybe this was some mistake. Production capacity, what you can say is right. Yeah, so this is the daily demand, but rasmalai have unlimited demand, but we have a production capacities that we cannot do that. And one more constraint is that this is the interesting constraint. So halwa plus 3 times of that rasmalai, which it requires that maximum we can use that only 600 liters of milk. We can use that, or 600 boxes combined together. We can say the 600 boxes combined together of halwa and combined together of rasmalai. We can build only that the milk quantity available is only for 600 boxes. So not more than that. And now still this is as I said, that implicit constraints are as usual more than or equal to 0. That's okay. Now this one is going to be the 3-dimensional. That's what they went for, a 3-dimensional one. Whenever 3-dimensional they went, see, look at that, the complexity of the solution is still it is increased. So you can have this, maybe this is the best combination. Maybe you can say that 0 combination of this burfis, and halwa is the 300, and 100 is the combination of rasmalai. Maybe this is the good combination. It might be that one, because they are using, see, look at here, x and y and z. There are 3 dimensions they have taken. They try to figure out all these particular combination of vertices where you are able to get that better optimized value. So this might be that optimum value. Maybe 3,10,000 is that better one. So here, see, look at these kind of problems when it is the outcome of variables are increasing, the complexity it goes such a way that it is out of the hand. So that's the thing. Only we will build that linear programming model only, this mathematical model, other than a standard algorithm. This is what they're talking about. I think it's clear about it, right? Is it clear?
Yes, sir.
Now the situation is, what type of questions you can expect during your maybe end-term examination. So what type of questions you can expect it is, so whatever that this particular sweet shop story you have seen, because earlier pattern of question paper only I'm talking about, where the professor will always focus on, there is a story they will give it. This story, it contains that a bakery story. Maybe, they are trying to manufacture a different varieties of cakes. That's variety of A and variety of B, something like that. Similar way, there is, another kind of maybe another kind of product. They will talk about some other product. Maybe they'll talk about a leather bags. Maybe they're trying to manufacture their leather bags. Maybe they talk about 2 different courses. So the courses requires a constraint of that, how many faculties required, how many labs are required. Such kind of stories they'll build it. After making this particular entire problem statement, they will ask you a question, identify which of the following is invalid constraint. So they might ask you that it might be that MCQ question or MSQ question. So if this MSQ question, they might ask you that multiple wrong constraints or right constraints they'll give you. If it is MCQ question, 1 wrong constraints they'll give you. So you need to identify. That's it. Don't expect that they might ask you that what is this feasible value, something like 1,90,000. They never ask you in that way, because so such kind of calculation, it doesn't make a sense, because linear programming model is only the model is built. We don't target of that what value we are going to achieve it. So I think you can check your PYQ. Yeah, tell me.
Sir, so the type of questions you are saying, could you go to the PDF ones?
Yes. This is.
Could you go to the previous page? So you said incorrect means like here 400 is the maximum capacity, and in options they might give in addition the answer would be like across 500, so that you should choose that one.
Yes, they might give you that. See, look at the milk constraint is there, right? Okay.
Yes.
So
sir.
what they might ask you, the milk constraint is, so halwa plus 3 times of milk required, 3, 1 halwa box, you have that 3 kind of rasmalai it requires, less than or equal to 600 is the right constraint, right? Is it right constraint?
Yes, sir. Yes,
that's
sir.
Because it is that's going to be, maybe they will ask you here 600, they will like this. So halwa plus 2 times of R, so this is a wrong constraint, right? Because it's a 3 times, right?
Yes, sir.
So this way you need to identify this is a wrong answer, wrong constraint, because as per the question we found it is 3 times milk requirement, but here they are giving only 2 times of milk requirement. So that you need to identify. Is it clear? But only the story is different. Like bakery story, they might ask you some leather bags, courses, something like that. Okay. But they don't ask you that what is the maximum profit, what is the minimum loss. They never ask you that, right? Is it clear? Yeah, because I'm taking
Yes, sir.
that earlier pattern of question paper. Yeah, that's it. Yeah, that's okay. That's okay. Up to this, these two particular versions of problems, what you have seen is that these are all integer optimized value we are getting. Maybe whatever the combination values we are using, integer optimized value. That, like, maximum profit and minimum or constraints what you are defining. So using it, we get that accurate results. We are sure accurate results. But let us consider the next problem. The next problem is somewhat typical. So here, this is hand woven carpets problem, where it contains that each variable is a subset of another collection of variables. I can say that earlier we have seen that this particular halwa, barfi, and then rasmalai, all these are one variable only. But here we can say that it is a, what you can say that, we can say that, a variable is a vector, or you can say that array. We can say that because already we are familiar with array, or you can say that vector of values, which is a collection of sub values inside. In that case, dynamically the values are changing. So in that case, some kind of interesting thing it happens. You may not get it accurate results. We may not get, because here accurate results we get it, but here we may not get accurate results. This is the one example where we are trying to solve with linear programming. So yeah, this is called, as I said, dual LP problem. What you can say that a dual variables represents that a marginal effect on the primary objective. There is a different effect on the objective what you are achieving. You may or may not get that accurate results. Let us see. Let us see. Because of that, dual LP, you cannot say that one variable contains only one value. It contains a collection of values inside. Let's see this. There is another interesting problem, which is hand woven carpets. 30 employees, they are producing 20 carpets per month. That is the capacity of that entire employees are working in the manufacturing. And the salary per month is 20,000. So the labor cost for the carpet is going to be 1,000, because 20 carpets you are making in a month. So one carpet cost is going to be that labor cost. It's going to be that 1,000 rupees. That's what actually we do that. But what happened is the demand for that carpet is not always the same. Right now, maybe this month is 20 is okay. Next month, when the winter season or some other season it will come, you might have to increase, or some other festival season. Maybe we don't know. So at that time, the demand is changing month to month. So that's the thing. There is a seasonal demand. So what happens, this is a dual variable. This variable, it contains 12 values. Month 1 demand, month 2, month 3, month 4. So all 12 months demand is there. Similar lines, whenever demand is there, we try to take the overtime from the employees. Whenever we take that overtime from the employees, we pay 80% extra. Maybe 1,000 rupees per carpet we are paying. No? Additionally, every new carpet we need to pay that 800 rupees extra. Additionally 80%. No? Actual cost is 1,000, 80%. But we take 30% of time only allowed. Overtime we are giving to that. But additionally, if they work for the 10 hours a day, Only overtime they can do another 3 hours only. That's it. That's the one constraint. So here, one more thing. So whenever 30% only allowed, what about other demand we can produce? We need to hire some particular another new employees. We need to hire them because the demand of this next month is going to be high. So immediately the beginning day of the next month, I try to recruit the new employees. Whenever you recruit a new employees, what you have to do is there might be a pre-training to be given where you need to do an expenditure of 3,200. Similar way, we are trying to lay off the particular employees whenever demand is less. No demand, we are trying to firing out the employee. When you are firing out the employee, we try to give some kind of bonus where they are leaving like you empty hands. We are not making them to leave. So that one we are giving 4,000 rupees per employee. So here still one more. If any surplus carpets are there, this month surplus top carpets are there, we try to send out to the warehouse where the warehouse charges are there 80 per carpet. So all these are whatever you have seen, all these are, it includes that a set of values of that 12 values. Is it right? Is it right or not? Is it right? It's not a one variable. Hello.
Yes, sir.
It is a collection of 12 values. So where it
How?
Yeah, it is pretty simple.
Or D1 to D12. Yeah,
correct. Because it is a January to December, you will have the different demands are there. Is it right?
Actually, the company is a carpet selling company.
Carpet manufacturing company.
Carpet manufacturing.
This is demands. Okay. Similar way, we do hiring and firing, right? Is it right? So let us consider this is a demand. There is a hiring kind of array is there. It also contains that 1 to 12 values. Is it right? Similar way, there might be firing also you need to do. So for that, you need to have that different kind of 12 values. Similar way, we have that one more. Yeah, this is okay, this is okay, this is okay. Yeah, hiring, firing charges. Yeah, this is carpet storings we do, warehousing, right? This is warehousing. Because every month there might be surplus carpets are there. So that carpets we try to store it. If no surplus carpets, this particular warehouse quantity is 0. So this way it is maintained so that every variable, it does not contain only one value. It contains that multiple values. That's the thing we call it as dual variables. So when you go dual variables, you can see the interesting thing here. See here, workers in a month, that's called I. Assume that W0 is the first month where it is 30. Next month onwards, the worker strength may be increased or decreased based on the demand. Similar way, the carpets made in the month based on the demand, they might be increased manufacturing or less manufacturing. Similar way, overtime carpets are there because their price is different, 80% extra. Actual carpet making is the 1,000 rupees, but extra OT carpet, if you are making, the cost is going to be 80% extra. That means it's going to be that 1,800 rupees. Similar way, we are hiring that and employees for every starting of the month if it is required. If it is not required, we try to do firing also. Is it right? These are hiring and firing. Similar way, surplus carpets are there. We try to store them into the warehouse. All these are contains that 1 to 12 values. Is it right? Is it right? Hello.
Yes, sir.
Yes, sir.
That's the reason it's totally 72 variables you are using. It looks like W, X, O, H, and F, but each one it contains that again 12. So 72 variables plus W0 and S0 because the starting month variables are always we are fixing. Totally it is going to be the 74 variables combination we are using. So here if you go for constraints, these are all the constraints. You see that. So starting month workers are 30. Starting month carpets are 0 because there is no storage. Assume that the first month is just a empty month. We don't have any storage. So every I represents that 1 to 12 months. That's absolutely we did it. And implicit constraint is there always value of this particular each variable and dual variable is going to be that non-negative value. And now, so look at that. So this is what exactly 20 and then workers. This is carpet made regular time plus OT time. Regular time is there, OT time how much they can use it. They can spend, I think, yeah, this is OT time extra is 20%. This is okay. Wait.
30% overtime.
Sorry, this is 30%. I have to given something right, Yeah, that's okay. Yeah, 30. And next one is you might use that number of workers in the current month. We do that existing workers, and there might be hiring and firing. We use it, right? H of this high minus F of this high, so that hiring and firing. So regularly we do that. Similar way, earlier stock actually it is not stack. Earlier stock plus production minus demand. So whatever that remaining is there, that you have to put it in the storage, which is called warehouse. And OT production is 30%. That is 20 of that 6 at most. How much it is. This one is actually, we don't say the exact value, but it's okay. It is at most it is 6. So here, what we are trying to objective is minimize the production cost. If production cost is minimize it, we can achieve that maximum profit because we can fix a good price to the selling price. Then we can. If production cost is high, the selling price is going to be the high. So maybe you may not achieve the maximum profit. That's the thing. We try to minimize the production cost. That is what our objective. Is it right?
Yes, sir. Sir, sorry to interrupt. There, which you changed to 30, it should be only 20 only, right, sir?
Why it is 20?
Because 20 plus overtime, right? 20 carpets at least.
Correct.
Overtime would be other.
Correct. This is
which should be less than 6 at least. Sorry, at max 6.
Correct. This is 20. Yes. Correct. This is 20 only. Here it is 30%, which is 20. That's right.
30% of 20.
Correct.
Yeah.
That is 6. Okay. Yeah. Got it. Yeah. This is okay. But what happened is this is our final objective. But the thing is, what really happens is if you go for that scenario where it is we are trying for an optimum value, optimized value, you might get a fractional values. Why it is fractional is maybe you need to hire the particular workers 10.6 based on the demand, because the demand of the next month it is increased to this. So based on it, I need to hire the employees 10.6. Is it 10.6 possible to recruit human resource? Not possible. Is it right? It's not possible, no? Yeah.
Yes, sir.
So either you have to go for upper limit of 11 or you have to go for lower limit of 10. If you go for a lower limit or upper limit, due to the upper limit, you need to pay over. Due to this, we are getting a payment of less. But what happens is accurate results, we cannot get it. Accurate production cost, we cannot get it. Because of this particular linear programming, sometimes it is not suitable for this kind of fractional problems where you are getting that some fractional value where it is not possible to make, rounding off the realistic number, the nearest integer. If you recompute the results, it might result that result is larger value or small value. So whenever you go to the larger value, the production cost is increased. Whenever you go for a smaller value, accurate production cost, we cannot get it. So that's the thing. Based on this, the linear programming of this particular kind of problem, it is not suitable. So earlier two problems, it is worked well because it belongs to the production. But this one, it belongs to the hiring and firing, which involves that humans, where you cannot have that any kind of fractional values. I think it's clear, right? It's clear, right? Hello, is it clear? Yeah.
Yes, sir.
But this problem is proving linear programming is not suitable for a kind of fractional values, real values. But the next problem is there, where the linear programming is suitable, where you can see that a bandwidth allocation. You can see this one. See here, the bandwidth allocation is there. Here also another problem they are talking about. There are three users are there, A, B, C are connected to each other, configured through switches. Actually, the small A, B, C are called as switches. We can say that ISP provider which is providing. And link have the capacities there. This is called edges of the capacity. Each connection A to B, B to C, A to C should have at least 2 Mbps line. At least. More than that, no problem. So least is that 2 Mbps speed is required. So direct or indirect connections are allowed. That means if you want to go for A to B, we go through the switch small a, small b, then B. So similar lines. So if you want to go for, go to for C, or you can go for it A and then small a, then B, then you can go with B in this way also. Maybe I think A and C in this way. This is also no problem. This is also no direct way or indirect way. That's okay. Now, each connection earns the revenue. A to B, we are getting that rupees of 300 rupees per Mbps. B to C, we are giving it is 200 Mbps. And A to C is there, which is a costly one we are giving 400 Mbps. This is clear because highest cost we are charging. A to C, that means maybe this path. This path is most cost. Is it right? This one is the more costliest one. Now, the variables, as you know that every connection has two routes are there. So directly that the route X is there, A to B, and another route is there, that's indirect path also there. Similar way, B to C direct path is there and indirect path is there. That's going to be okay. That's fine. Yeah, that's okay. Now, there is some constraints are given. See, I think if you could see that the constraints which are there, which is representing that this particular link capacity, this particular line, it can have the maximum bandwidth of that 10 Mbps. This line have maximum bandwidth of 6 Mbps. That's called maximum bandwidth, right? So combined of that, every constraint is based on that, this is XAB and YAB plus XBC and this three, maximum less than or equal to 10 Mbps line only, because a direct path or indirect path, X is nothing but a direct path and Y is nothing but an indirect path. So this line, maybe this is, they're taking is then maybe this path. Similar way, other path is there, it's a 12. And other path is there, which is going to be 8 because for the C, correct. Yeah, that's fine. So this is A to C direct way, or A to C indirect way, B to C direct way, or B to C indirect way. That's maximum constraints they have given. So here, there is switches also, there are having constraints, right? There are switches are there because internally switches have some capacity. More than that, we cannot go with it. So that's the thing, internal switches also they have taken. Of course, these things, simply we can say that the constraints which are made based on the problem. Here, the solution we got it is this one. And understood, the solutions which you got it, here it is okay, that integer solution. Here we got it 1.5 bandwidth. Here it is 4.5 bandwidth. Here it is 0.5. That's okay. But here we are getting a fractional values. Even fractional values you are getting, these are valid because it is a bandwidth allocation. So bandwidth allocation doesn't create any problem because so we can go within a fractional value. So it is proved that the same linear programming model works for some kind of problems where that quantities we can represent with fractional, the real numbers. But earlier problem is there, which is not giving accurate results because of the linear programming model is returning, fractional values. Due to that, accurate results might be missed. So I think you understood, right? Where that linear programming model
Yes, sir.
will pass and will fail. Sometimes it will pass and sometimes it will fail. But the only thing is it's all only which problem is able to solve it. If you have been worked out and figured out that a mathematical model with list of constraints, but sometimes at the end of the particular solution, you might realize that this problem does not give you that accurate results. Due to that, we don't go with. So maybe that particular way, which you have seen that carpet manufacturing, where you may not get it accurate results, even it is solution is an exponential one. I think, yeah, up to this is clear, right? Yeah, mostly linear programming question, which you can expect is what I said that earlier is the same. Only they'll give a story of it. Based on it, they'll have a list of constraints, either MSQ or MCQ. We'll ask you that identify whether it is wrong constraints in MSQ format or MCQ format. Sometimes they'll ask you that right constraints also. Yeah, tell me.
Consider go back to the PDF.
Yes. Correct.
Sir. The answer is coming as consider.
Correct.
Consider the tail end link B small b to capital B is 0 plus 7. You are summing up all the values, but you are left behind two values, 1.5 and 0.
Correct.
0.
Correct. The maximum is 10 allowed, no, right? So small a to capital B, that is root this one, right? This one is okay, 10, no problem. But thing is, the bandwidth maximum you are giving solution, right? So A to B direct path is 0, A to B indirect path is 7 bandwidth. Clear? So B to C direct path is 1.5 Mbps, B to C indirect path is 1.5. So if you can see the charges revenue we are achieving is, we are achieving maximum revenue from this and this, right?
So sir, X is direct path and
Y is indirect path. Okay. So here maximum revenue we are getting from this A to B and A to C, right?
Yeah.
So that's the thing, we try to allocate a maximum bandwidth for this, right? Okay. So less bandwidth we have given for B to C because we are getting 200 rupees Mbps, right? That's the thing. Maybe that constraint is we use maximum revenue because revenue also maximized. Wherever we are getting that more subscriptions and more amount, there we try to allocate more bandwidth, right? Yeah, that is a strategy of it. Okay. Okay then. Yeah.
Yes, sir. But here you are choosing one of the largest revenues and the rest one is the smallest one.
Because we have to maximize that profit, right?
Because there is a limit of the profit maximum. You
can't
go beyond that.
No, we can go for it. But thing is, maximize, what is the technique they use it to maximize the revenue? Wherever the subscriptions you are getting more amount. So here, they already given subscriptions, right? Yes, here is. Yes. So each connection earns a revenue. This is what, right? So that's the thing. We try to use this. A to B is 300 Mbps. We are getting it as 300 rupees per Mbps. A to C, we are getting 400 rupees per Mbps. So we try to allocate more bandwidth for this, right? Clear?
Yes, okay. A to C for our maximum profit or revenue.
Correct. To achieve the maximum, because that is the objective, right? Two objectives are there. We try to achieve that revenue, more revenue we need to achieve it. That's the thing, to achieve the more revenue, we try to allocate this bandwidth in this way. If we allocate in this way, the subscribers are going to get that at most quality. Clear? Yes. But here, the allocation, you can be the fractional, no problem. Is it right?
Yes.
But earlier it is not okay because that is not accurate result, right? So linear programming model, it works sometimes with only integers. Sometimes it works for that fractional values also. The problems which it requires the solution in fractional also it works. But some problems are not suitable, like earlier problem which I have done, where it is not suitable for solving through linear programming. Okay? Yeah. Is it okay?
Yes, sir. Okay.
Now, this is the question you can definitely expect, because I have seen that earlier pattern of question papers. Always they try to maintain the same kind of story, like, maybe they'll change it, some outline novel or some kind of story, they will change it, but at most they'll ask it invalid constraints or valid constraints, which of them, MSQs or MCQs only, they will ask you. Yeah, this is okay. Yeah, that's okay. Now, yeah, this is the first part of it. In the week 11, there are various parts we need to discuss. The first part is the linear programming. Second part is that network flows. This is another interesting part. Of course, third part is there. Maybe if time supports that today, we'll go with it. Yeah. So network flows is another interesting approach of solving the problems. See, actually, yeah, there is a real-time scenario where you definitely use that network flows approach. So you can have this one particular scenario. This is another approach of solving problems. There is a oil network is there. So this is simply a oil network. There is a source node is there. A sink node is there. A target. This source node will get that input from some kind of source. We don't know what is that. This sink node, it will send its final flow to a target. We don't know what is this one. We don't worry about the capacity of this one. We don't worry about the capacity of outgoing. We are worrying about that the maximum flow allowed from source node to sink node. Maximum flow. Remember, this particular vertices has no storage. Again, I'm telling you that no storage. No storage. Whatever the flow is there, that flow it has to send it as it is. The pipeline's capacity is defined. The orange color represents that. The edge weights represents that. The pipeline capacity, maximum capacity. We don't have any storage in the vertex A, D, B, C, and E. Whatever flow is there, it's picking out and it is sending. The maximum flow allowed from source vertex to sink node. The source vertex is here. Source vertex is here S to sink node T. What is the maximum flow allowed? Maximum flow allowed. So it is pretty simple. So what way it is simple is, so here, what is the incoming flow? It is there, but outgoing flow only we are worrying about. We are not worrying about this. We are not worrying about this because we don't know what happens after T. We don't know what has happened before S. That's why we don't worry about it. But here, the outgoing flows are there, 2, 1, 4. So what is the total of this? What is the total of this?
7.
Correct. So there is incoming flow is there for T. So what is the incoming flow? Total?
7.
Correct. So based on the 7 and 7, directly can we say the maximum flow allowed from source vertex to the target vertex, that is T, is going to be 7. But is it a right answer? Definitely not. Not sure.
Might be right, sir.
Might be right,
but not always.
Not always correct. Okay, might be right. Why it is might be right is, let's have a different colors. Whatever the 2 it is flow, it's coming. This 2 it is picked here, and from here it can send to here, and it can send to here. The flow 2 is over. Clear? Is it over? No? The capacity, this is over, this is over, this is over. Is it right? Is it right?
Yes, sir. Yes, sir.
Now, so 1 flow is coming here, 4 flow is coming here. So let us take the 4 flow. The 4 flow, it is coming here, and it is coming here, and it is going here. So I can say the remaining is here 1, here it is 1, here it is 0, because no more, 4 is already used. Now, so another 1 you are taking, if you go this 1 here, this way, after going for D, D to C, and again C to E, E to T it can go. So that I can go with another color, which you can say this color. So this 1 is going here, then here. After that, it is coming here. After that, it's going here. Then after it, it's going here. So this way, 1 is gone, 1 is gone, 1 is gone, 1 is gone, 1 is gone. So that this particular 7 is perfectly, it's okay, no problem, because that's what they're talking about. Yeah, this is what they're talking about. Ship as much as oil from source vertex to sink node. Sink node means T, target. No storage is available in the way, because each particular vertex, whatever incoming flow is there, it tries to send it to the outgoing. Maximum capacity of the pipeline is edge weight is defined. We cannot send more than that. Less than or equal to capacity is okay, no problem. So a flow of 7 is possible, because we are easily telling that's okay. Is it the maximum flow? Definitely it may or may not, but always it's not right. Check the out degree and in degree of that S and T. So out degree of S, in degree of T, we checked it. So based on it, we figured out. So what is the maximum flow? That we said it is 7. But also do the check in and out degrees, which are going to be local vertices. Local vertices means this A, B, D, C, and E. Inner vertices, inflow and outflow also you need to check it. Then only you can validate that maximum flow. I think you understood what is a network flows. Is it clear? If
Yes, sir.
yeah, if it is clear, we'll go that other graph, whatever the next graph, where you cannot estimate directly. This is that. You see that here. So if you could see that here, based on this particular, incoming and outgoing, what you can say that the outgoing flow of T and outgoing flow of S and incoming flow of T, we cannot justify that this is the maximum, because we need to carefully check it that each one. So let us take this graph is same, but the edge weights are changed. Yeah. So as I said, this source and sink nodes are special nodes where we don't worry about these. The capacity of that each E, that is called CE. That means the capacity of S2A is 3. The capacity of S2B is 3. The capacity of that S2C is the 4. That's what called capacity. The capacity of each edge. The flow of each edge is called E, where that FE is always less than that equal to the capacity. For example, the capacity is 4. You can have a flow less than or equal to 4. No problem. That's called FE. FE is nothing but current flow. Capacity is the maximum. So you can have, so less than or equal to that FE can be less than or equal to C. No problem. So, but make sure sum of incoming flows are equal to the sum of outgoing flows. That is more important. If you carefully check it, that it works. For
Like
example,
you can go from S to T in the way S to C to E to T, and you can go from S to B to D to T. It will be
correct,
more efficient.
correct. See, let's check it. Let's check it. So what is the incoming flow for A? 3. Is it right?
Yes.
So outgoing flow for this A is 2 only. So that means we cannot take the 3 flow from this particular S to A and we try to send it from A. Is it right?
Yes.
We need to send only that. So 2 flow to the A, immediately from the A I can send 2, no problem. Similar way, this 10 is there. If you take the 10 incoming flow for A, can we have an outgoing flow 10? No chance. It's not there, no, right? Right?
Why, sir? Because
If it is 10 is coming, where can I send this 10 flow outgoing? From A? No chance, right?
because
Yes, sir.
because they have storage capacity.
No, we don't have. That's what they clearly said. Every vertex has no storage capacity.
So how A is storing the rest of the 8?
No. See, that's the reason. So make sure that maximum flow allowed is that based on that internal checking of each incoming flow and outgoing flow. You need to check it. So what is the maximum flow allowed from S to A, S to T? We need to identify. This is our target, right? So to identify this, we earlier graph is pretty easy. We have been find out, right? Already just 7 we are finding. But this is not easy. We need to figure out that each particular flow. So first it is we are taking maybe the flows which you are taking. We'll try with the flow of maybe you're taking 10. Whatever 10 is there, right? This 10 can you take, no, right? Can we take the 10? 3, 3, 4, can we take it?
Yes.
So if you take 3, 3, 10, this 10 flow maximum allowed, just check it. For example, 3 is taken here, 3 is taken here, 4 is taken here. So if you take 3, 2 is gone. What about the next one? We cannot take it, right? Is it right?
Yes.
So that 10 doesn't work. Can we try with 9? Yes, let's try this. So if you take a 9, maybe you take a 3 and 3 and 3 or something like, that's your choice. So if you take a 9, maybe 4 as it is, you take it. Maybe you take 2 here, 2 you can take it here. Otherwise 2 you take it from this S to A, maybe you take this is 2. Okay, 2 and this 3 and this 4 if you take it. This 2 is going, once it is gone, the capacity is over. After this 3 is coming, 1 it goes here. What about the remaining 2? Can we go here? No chance. Because already this 2 is used, right? This 2 is used, no, right? Is it used? Already this path is used. If this path is used, this one will become 0, this one will become 0. Here it's remaining 1 is there. So that 9 also not suitable.
Oh, so how much you are receiving, you can't
send it. Because the maximum capacity, they clearly said flow allowed is less than or equal to its capacity.
Oh, so
that's
every time you have to flow out the lesser amount which you have received.
Correct. Less than or equal to. Okay. So next one, 8 can we try? I think 8 also not possible. Let's try this one, 8. So yeah, 8. So 8 if you are taking, maybe you try to take this one is 4 is okay. As per this one, we take it is 2 because we have to send it. So 2 and this one also 2, we take it. Maybe you take it then. Yeah, that's okay now. Yeah, now if you take 2 and 2, so in this way, if you are using, this flow is over. This flow is used. This flow is used. This flow is used. This flow is used. Now another 2 you are taking. Once you take this 2, what happens is
you can use the one, but
wait. If 2 is used, this is over 1 is there, right?
1.
Okay. But these are become 0, right?
Yes, you can flow out.
Fine. Now we are taking this another 2 because I said it is 8 is the maximum flow we are allowing. So when you are allowing maximum flow is 8, already 2 is finished. Another 2 you are passing from here, maybe. Clear? If you pass it another 2, 1 it goes here this way.
Yes, you can.
Another 1 it goes here. There is no way here, right?
Yeah, it's finished.
It's finished. So that we cannot do this job, right? So that 8 is also not allowed. Not. Let's try the 7. Let's try the 7. Yes. So yeah, that's try the 7. Correct. So if you try for 7, maybe what the better combination? Maybe you try this is 1. Yes, I can. 2 I can try because it is maximum is 2k. That's okay, fine. So I can try this is 2. Maybe this could be black one. 2 is already used. Correct. Next one. I'm trying for 7 now, right? Clear. 2 flow is used. Still, I have that 5 flow is there. I can send 1 here. Can I send 1 here, right? Yeah, I can send 1 here. So if I send 1 here, so 2 is the remaining. This I can use it. This I can use it. This I can use it, right? This I can use it. No, this 1 I can go this way, right?
How? Because you have no flow.
It's there. D2E is there flow. D2E is there, no, right?
But you can't do nothing with that because you have already used.
We can do here. 2E is coming. Clear? Sorry, I'm sorry. Just a minute. I will erase this one. Maybe. Yeah, this flow. Already this flow I used it. Yeah, this is 2 is already used, right? This flow is 2 is used. Now I'm going with another flow. Another flow is this way I'm going with 1. Okay. Can I go in this way?
Yes.
Because already
we can go to C, sir, if we want.
B to C I can, B to D I can go, no, right?
Yeah, B to D, from D to C also we can go.
D to C also we can go because one capacity is there, right? Fine. So that in this way, if you go, this one will become 0, this one becomes 0. This already we have used it is 1 only. I have the remaining 2, right?
Yeah.
So this flow, it requires that capacity of 1. 1 is over, right? So this way, sorry, still blue goes there. This way I can use it. So in this way, if you go here, it's 4 is pending, right? 1 is already used, no? Is it there?
Sir, 1 कैसे यूज होगा? आपने तो खर्चा कर लिया 1.
Yeah, it's what this is over. 1 flow I'm using. This is over. But 5 minus 1, still 4 is there, no, right? Still 4 is there.
4 is available. Okay, available to.
Available.
Yeah.
To the next flow. Next one. After this particular one is this 2 is over. This 1 is over. 2 plus 1 flow is over. Next one. Another flow I'm making is the 4. If I move the 4 is here, this way, is it okay? Allowed? Is it allowed or not? So in this way, if you go, so that 4 can be achieved, like 4, and it will become 1 because after removing 4, this will become 0. So that it's going to be 4. So 7 is a valid. Perfect one. So maximum flow allowed from S to T is 7. But it does not mean that based on the source and based on the sink, outgoing flow and incoming flow of source and sink. It is based on that internal checking of that each particular capacity. So here you check it. This is the linear programming constraints. So please remember these things. Yeah, this is. Yes. So as I said, variables FE contains that flow of that each edge. Flow from S to A, flow from B to D, flow from C to E. So that is called flows. Like your example, 3 values they have shown, but you have a multiple values. That's called flows. Upper bound is defined. Upper bound defined for each flow. Example. So flow of that FB definitely B to A definitely must be less or equal to 10 because you can check it. Just let me erase this one. I'm erasing. The maximum capacity from B to A flow is 10. So that's called FBA. You can check it. This is FBA. FBA means the flow, it is less or equal to 10. Is it right? Is it right? Outgoing flow,
Yes,
right?
Sir.
Upper bound. And
Yes, sir.
Conservation flow is there. That is different called, upper bound. So FAD plus FBD must be less than or equal to FDC, FDE, FDT because incoming flow and outgoing flow is there. So less than or equal to outgoing flow is fine because 2 plus 1 is less than or equal to 1 plus 1 plus 2. So if you can see that FAD and FBD, this is called FAD, FAD, okay, this is FAD, clear, plus FBD, this is what? FBD, this is FBD, must be, these two sum means 3, is it right? FAD and FBD sum is what? 3, is it right?
Yes, sir.
It must be less than or equal to FDC, FDE and FDT. These three combination is because incoming flow and outgoing flow, they must be less than or equal to that. Then the things it works in smooth. That is what it works. The conservation flow, it matches to this constraint. Then only you can do it. Otherwise, you cannot do it. If incoming flow, for example, if you consider this, see this one, FSA, FBA is there. These two are there. FSA is there plus FBA is there. Is it less than or equal to? There is outgoing flow is there. That is what? Flow of that FAB. Is it true or false?
FSA plus FBA is equal to FAB.
Yeah, because outgoing flow from A is only one. So it is not happened. So this is going to be false. Is it right? So that we cannot take flow.
Also, there is no flow between A to B.
A to B, there is no flow. B to A is there. Clear? Because it's a directed graph, right? It's a directed graph, right? So this constraint, if it is not satisfied, we cannot do this flow. We cannot use this 3. We cannot use this 10. If this 3 maximum, I can use 2 only. I cannot go more than that. Is it right? This 10, I cannot use never, right? Because if we take a 10 incoming flow to the A, where can I send this 10 flow? I cannot do that, no? So that particular conservation flow constraint, you must satisfy this one. So incoming flow and outgoing flow, incoming flow can be less than or equal to the outgoing flow, no problem. If incoming flow is higher, outgoing flow is less, you cannot do that. Hope you got it, right? Is it right? Is it right? That's the thing. They said, don't depend on the source and sink node. You try to verify that each internal vertices, what is their incoming flow and outgoing flow. If you identify the incoming and outgoing flow capacities and flows, you can easily figure out that maximum flow. Here, definitely you can expect that, yeah, this is, this is a simplex way is exploring, earlier whatever you have done, just it is exploring all the paths where it is maximum flow is allowed. That is the easiest way because whatever you have done earlier approaches, I tried with 10 flow, I tried with 9 flow, I tried with 8 flow, but finally I got that value of that 7 because 7 is the better flow where you can achieve the maximum flow allowed. This is a linear approach model. And one more thing is, definitely we can expect a question in this particular concept. What way they will ask you is, they will give a graph to you like this, whatever graph is there, this graph they'll give you. They ask you a question, what is the maximum flow allowed? The easiest way is doing whatever approach I said. You try to investigate, first flow is this, second flow is this, and third flow is this. The total it is allowed is this one. Okay.
Sir, I feel we need to include the minimum edges first. Like the constraints are minimum, like ones are causing, like
Correct.
ones and twos will cause some constraint problems rather than 3 and 4. So we should first make a path through ones, including, like not including all, such that it becomes common, like from BD and BC both are same. So we can remove one of them. and we can include AD DT, so which is also in the solution that way.
Correct.
After that, we can like choose go to 3 and make a form from 3 to 2. So there only 2 will be going instead of 3. So from 4 to 5, in that way, I feel like it's like modifying MCST, like minimum cost spanning tree, not actually that.
But a
Yeah.
linear programming approach is pretty simple. What I feel is, if this path I'm choosing, for example, S to A to D, and D to T, all this path, what is the minimum edge cast is there, that I'll select. Clear? For example, this path I'm selecting. This path is this one, right? Okay. So what is the minimum edge cast here? 2.
2, sir.
So I can select this. So it will go off. It will go off. Remaining capacity 1 is there. Don't worry. Already 2 we got it. Next. 3, if you take it, it's not possible, because this way if I'll send, this way I'll send it this way. So I can use it a different color, where I can do that either this way, and this way. In this path, if I choose it, what is the minimum edge weight is there? 1. Is it right? Is it right?
Sir.
So I can choose that 1, so that this is gone, this is gone. Yeah, this is will become 4. This one will become 4. This one become 2. So that this complete one, already 2 we got it. Already 1 flow we got it via green. And the last one I'm figuring out is 4. This 4 is the last one, because S to C, C to E, and then E to T, directly it's a 4, 4 is gone, will become 0. Here it is saturated, no chance of it, because there is no outgoing. Here it is saturated, no chance of going. Here it is saturated. Here it is saturated. Here it is. So once it is saturated, we don't have a chance of flow. So we got already 2 plus 1, and this is 7. This is a simple kind of thing. Only thing is, we give a graph and we try to ask you that what is the maximum flow allowed from source to sink. That's it. Is it right? Is it right?
Yes, sir. Yes, sir.
But actually, in the revision session, we'll discuss maximum flow allowed and minimum cut also there. There is a question, is there? Anyway, at the time of PYQs, we'll discuss maybe in the end term revision session. That is an interesting question. They'll give a graph. They might ask you that same graph. One is the maximum flow they'll ask you, then they will ask the minimum cut also. So you will understand, even in the Madhavan professor, he said about
yes, sir. Yeah.
Minimum cut and maximum cover also he has asked, like a CC camera scenario. He talked about it. That anyway we'll discuss about it. I think yeah, up to this is clear. Any clarification? Is it clear?
Clear, sir.
Now this is a easiest and simplest way to figuring out. This is easiest way, because it is a linear way we are trying with all combinations with 10, 9, 8. So what is the maximum possible value we are able to flow? Path 1, path 2, path 3, 3 paths. So that we are figuring out. But is there any other different way to get the solution? Yes. That is called Ford-Fulkerson algorithm. The mathematician Ford-Fulkerson, he said, that particular linear programming approach is okay. That's okay. But there is other way of doing also there. So what is the other way of doing is this one. That is called residual edges we are drawing. What you call, reverse edges. Reverse edges. Why do you use reverse edges or residual? What you can call it as residual edges or residual graph. Anyway, we'll see what is this one. Yeah, you can see this one. By seeing of simple graph, you can identify what is the maximum flow allowed from S to T. What is the maximum flow allowed?
2, sir.
Correct.
2.
This path is 1, and another path is this, right? So maximum is flow is 2. This is okay. That's pretty clear, because S to A to T is 1.
I think 3 is also, because you can go S to A, A to B, and B to T.
No, we cannot, because once you have used this path, this is saturated, this is saturated, this is saturated, this is saturated. No further flow, right? It is already zero.
If you
Once,
first time visit S to A and A to B and B to T, then it will be 3.
no, not 3.
It
No,
will be one.
one flow, it is moving towards the 3 edges, right? It will not be 3, right? Maximum flow allowed in this way is weight of 1 only, right? This is the capacity.
Yes, sir. Yeah.
Okay, yeah. But thing is, yeah, this is okay. Just a minute. Yeah. Here, this approach which you have said it, right? S to A and A to T is a one flow. S to B and B to T is a one way. So this is a clever way you are choosing, because you have been simply you're figuring out this one is a cover. But for example, there is a choosing a flow which is not a clever approach. For example, I have chosen I've chosen a bad flow. A bad flow means something like this. For example, what I did is this path I have chosen. When I choose this path, this is saturated, this is saturated, this is saturated. Due to that, maximum flow it went for only one. This is no utilized, not utilized, right? Here this is not utilized because of bad flow you've chosen. See, look at here. If the flow is not clever flow is chosen. Not clever flow means S to A to B, B to T. Due to that, this is underutilized, this is underutilized. S to B is underutilized. Yes, but actually maximum flow allowed is the 2. But due to that bad flow you have chosen, we have noticed that one flow is unutilized. This is the problem whenever the choosing of the flow is incorrect. How to overcome that? Using that residual edges, or what you can say that reverse edges we are using. Reverse edges. So you can see that that's what they're talking about. Even the bad flow you have chosen, you can utilize the maximum flow. How it is, this is the way. Yeah, this is allowed to add the reverse edge, is able to undo that earlier flow. Due to the reverse edge decrease becomes 0. See, look at here. S to A we have chosen it is already flow. A to B have chosen it. B to C. Due to that, these are saturated. Is it saturated? Saturated or not? It's saturated, right? Is it saturated? Hello. Hello. This orange color is saturated, right?
Yes,
because of bad flow you have chosen. Then what you have done? A residual graph you have built. The green color edges. This one, this one, this one. The capacity of the reverse flow, reverse edge. After making reverse edge, I can choose a new flow, one from here, here, and here. Is it right? Is it right?
Yes, sir.
So if you have chosen this, another one flow is used so that it will become 0. This one will become 0. This one will become 0. So that there is no outgoing edges from S, because this is saturated, this is saturated. So already bad flow you have chosen is 1. This is 1. After that residual graph you have built it. Due to that we got another flow. So totally we got the flow of the 2. This is. Even bad flow you have chosen also, you can have a reverse edge for it. After making the reverse edge, you can try that one more flow by using the Ford-Fulkerson algorithm. So the same graph, they have given other edge weights also. I think you understood what it is. The residual graph is that. Is it clear?
Yes, sir. Sir?
Yeah.
Regarding the questions I would like to ask, I feel this is a bit complex. Like, would they insist to us to solve using this Ford algorithm, or
no,
like,
no. They
which
never
one is
asked.
good?
They never asked you to solve that using Ford-Fulkerson only. Because the solution is that simplex way you are trying with the linear programming model is very easy. Clear? Because more
Yes, sir.
conventional one. Ford-Fulkerson, again, you are drawing and we are solving, it takes time. Because if this is the graph, you need to draw that Ford-Fulkerson, it requires very much time, right? Is it clear? A bad
Yes,
flow
sir.
you choose, and again reversal edges, so it takes time because graphically you are constructing that doesn't make sense. Only simple graph they have given, that's okay, but they never asked you that use the Ford-Fulkerson only. Yeah, this same graph, but the values are changed because earlier 1 and 1 only they used it. Now they changed the values because to understand better. So you see that the bad flow is chosen. Actually, if the capacity, if you consider, the good flow is this. Is this a good flow? This is the first
Yes.
flow. This is the second flow. Is it right? It's a good flow. If it is good
Yes.
flow is chosen, the maximum, wait. Is it a good flow? 10, 10 is over. This is 10, 10. No, it's not a good flow. So what is the good flow? Let's see that. Yes. If 20 is taken, this 20 is gone. Yes. Yeah, that's fine. But even you have chosen the 10, 20, that's going to be that maximum 20 only. Clear? Yeah, this is fine. So in this case, if you try, maximum flow is how much? 20. Is it right?
Yes, sir.
Because it is saturated. It's a remaining 10 is there. It's a remaining 0. Another 10 if I take it, okay, there is no path from B to A, no chance. So we cannot have that. That's no chance. So the maximum flow is only 20. Even you tried that simplex format, because they never ask you to solve that using Ford-Fulkerson, but only to understand the Ford-Fulkerson. Even you try that a clever algorithm or clever flow, the maximum flow is 20. But if the same one I try with Ford-Fulkerson, so what I do first, I use that 20 flow from S to A to B, and B to T, so that flow is 20 is over. So once 20 is over, they try to go with a residual graph. So whatever the flow they have done, reverse edge they build it. Reverse edge means 20. This is 20 because if this particular 20 is gone, actually you are going back here. Actually earlier 20 utilized it. Remaining 10 is pending because the 30 is a capacity. 20 utilized it. Here 10 is there. The 10 is remaining. Similar way, this is the reversal, the green color, 20. And another 10 they are trying. So what another 10 they are trying? This way, 10 is going, and here 20 capacity is there. 20 minus 10, another 10 again remaining this way. So this is another flow it is taken. So earlier flow is 20. This using residual graph, it comes to that another this one 10. This is 10. This one will become 0. Yeah, that's okay. Maximum saturated. This flow is 10. So 10 plus 20, the total it is going to be the maximum flow allowed is 30. So it is saturated. No further flow is allowed. So it is at most we have reached. So that S to A is saturated, S to B is saturated. That's what S to A is saturated. S to B is saturated. So no further flow is allowed. So already we have achieved that 20 flow here. Using residual graph, we got it another 10. So totally we got is the maximum flow. Sometimes the simplex and clever approach also, you may not achieve the maximum flow. But where the Ford-Fulkerson has been figured out. Hope you got it, right? Is it clear? Yeah, actually, they don't ask you these kind of typical kind of thing. They're pretty straightforward. They try to ask you that a simple graph and try to ask you the maximum flow allowed. So, of course, along with that maximum flow, there is a minimum cut also there that we'll discuss in the revision session PYQs. Is it clear what I said until now?
Yeah, yes, sir.
Yeah, that's fine. Yeah, this is okay. Yeah, that's okay. But actually, the reductions is that next major concept. Once I entered, we cannot conclude the session. But quick recap: what I'm talking about today is whatever we discussed is first. Basically, we have started with the linear programming model. The linear programming model we talked about constraints is the more important thing, and we are achieving that using constraint. We try to achieve the objective, the optimized results we are trying to achieve it. So this linear programming problems we have tried it. We have tried that sweet shop problem in two versions. It's a two-dimensional one and three-dimensional one. And after that, there is hand woven carpets we are using. But this particular problem, uh, is not resulting that accurate results, because fractional results we are trying to round it to the nearest integer. That would result inaccurate results. So, but the linear programming is suitable for sometimes even for fractional results. Example is a bandwidth allocation. These are that three different sample sets of that linear programming. And there is a network flows kind of issues are there, network flows. Generally, the network flow issue we'll try with the linear programming approach only, which is a simplex format, which you tried it. We try to make it incoming flow must be less than or equal to its outgoing flow, then the flow is allowed. Otherwise, we don't allow. That is called the flow incoming is less than or equal to flow outgoing. Outgoing edges degree, we try to sum, and incoming in degrees, we are trying to do the sum. That must be less than or equal to the outgoing. That is the simplest way. But if you have chosen a bad approach or incorrect approach of flow, at that time you may not achieve that the maximum flow allowed. Incorrect or not a clever flow you have chosen. To do that better, we are using a Ford Fulkerson. But mostly I don't find that any kind of question on the Ford Fulkerson. Practically and problematically, they never ask you that. Mostly they'll ask you that maximum flow and minimum cut only, which is very frequent questions. Yeah, I think this is pretty much, because still we have one more session on the week 11, which you need to talk about some more advanced concepts. Yeah, I think you got the point, right?
Yeah, sir.
Yes, sir.
Yeah, good.
So, sir, how many topics are left behind?
I think two more topics. One is reductions is there, where the reductions is that one problem is helping to other problem, where you can reduce it with the help of other problem. And another one is there. There is classification of algorithms, where it is, polynomial problems are there. Non-deterministic polynomial problems, where it is NP hard problems are there, NP complete problems is there. So that is two more concepts are there. And 2 sat and 3 sat problems are there, satisfiability. Yeah, this is two more or three more concepts, right?
Yeah.
That's
So, when you are planning to do that
that is on Friday.
Friday?
Yeah,
Friday, you will come or some other instructor?
but that we cannot sure, because based on that allocation will come, right?
So, okay.
Okay, yeah, that's great. Yeah. But make sure that week 11 we can expect that mostly 2 or 3 questions more are theoretical, rather than that coding or approach kind of thing, right? Yeah, that's okay. Anyway, we have a revision session on the end term. At that time, we'll discuss
Yes, sir.
more problems on. I think revision session mostly on week 9 and 11 only. Yeah, that's it. I think end term revision session is on week 9. Week 9 is dynamic programming, and week 11 is again these things only we'll discuss. Okay.
Yeah, sir. These 2 weeks are very complicated weeks.
Yes, correct. Okay. Yeah, thank you.
Sir, this is, could I ask?
Yeah, tell me.
Will the end term would be on easier side, because quiz 2 result wasn't that pleasing to everyone?
Yes, sir. Quiz 2 result and
Actually, one shocking thing is quiz 2 paper is mostly from PYQs, but I don't know why the people are. I think imbalanced way they went. Even I have seen the top scorers also. The top 10% students also, they got less. That's what we are worrying about. Some questions they are asked, they are not answered in a better way. That's very shocking. Yeah, we can expect easy way. Definitely, we can have that easy questions.
And sir, in the OPP also, we are bottled in the OPP.
OPP is pretty easy. This time, I think OPP, I
Yes,
don't.
sir. Yeah, it
OPP
was
this time
easy.
is easy. But
Yeah,
quiz 2,
I scored full marks, sir.
correct. In quiz
Which
2,
set you have given?
no, OPP is easy.
Because sir,
All
in the fourth set, his questions are very tricky.
no. All the four sets that's having similar kind of weightage. I found that mostly similar.
I guess I gave it on Sunday, sir. I
Sunday it
don't
is,
know.
yeah, it might be then. Saturday also it's a one OPP was there. 2-1 and then 2-2-2. Yeah, I think 4 slots was given. Yeah. But end term we can expect very easily. I found that result of quiz 2. I think it's a 37 or 34 percentage. Even we shocked
Yes,
it.
sir. Yeah,
The
it
prof
was
the
so
prof
bad.
also shocked it why it was happened like that. He said he went through that again question paper, what he has designed, and he had a discussion with us. So that mostly questions are PYQ questions. Why this suddenly this drop out? I don't know. Yeah, this time we can
Uh,
expect easily.
Sir, a small query. This
Hmm.
is regarding again, like uh, compared to 21 batch, 24 batches content exam level is getting harder, or like what I wanted to ask is 21 batch had an easier
Correct.
uh,
It's
go
harder
through.
only. It's harder only because see
Okay.
the questions they are increasing that level of complexity because the professor insisted to do, because the final objective of the student is to achieve the good gate score, right? Because
Yes, sir.
he has to write that some kind of data science kind of gate examination. So always he tries to make the question paper at the level of at least 10 to 20% questions match to the gate level. That's the issue. That's happened. But the quiz 2 is recent quiz 2 is not like that. I went through the questions with all of the course instructor team also, along with professor discussion. Mostly questions are PYQs, right? But I don't
Yes,
know
sir.
what has happened. Okay.
Something happened.
But something has happened. But one more thing is the level of question paper complexity is little bit increasing. 10% variation is there. Tougher question.
Yes, sir. Yes, sir.
Yes. Because
Because
of the
I
gate.
feel
Hmm.
like I am doing 3 courses right now. I'm feeling I'm a standalone student. I'm feeling the pressure is there, but I
Because
see, yeah.
because the data science eligibilities are given for gate examination for BA students. That's the reason the complexity level is increased. Okay. Yeah.
Okay, sir.
Okay.
Thank you.
Because
Yeah.
we are not ending with only this. We are moving the students to the higher education. So that's the reason our BS degree, because professor is very particular about the PDSA professor. So he always targets about uh, the question. He tries to, uh, you know, give the reviews in a different ways. Like, some red color reviews he will give it, purple color reviews he'll give it. If he has given a red color review, you must be very careful because there is a big mistake and big, thing in the question writing or something like that. He's very particular about it. He doesn't compromise the quality of question paper. I found that since last few terms, right? Yeah. Even that revision session questions, he suggested to use the revision session questions are too complex questions than PYQs. Always he suggested to have a discussion on that. Okay.
Yes, sir. That creates a confidence also.
Correct. Okay.
Yes. Yeah.
Yeah.
Thank you, sir. Thank you so
Okay. Then
much.
bye. Okay.
But
Then.
sir,
Bye.
what
Bye.
I think, the
Hmm.
degree should restructure itself like a general college degree, because each and every term
Hmm.
for entering students, and there is something like very short of span of time students are getting to improve their skills. If they
Okay.
arrange only 2 semester in a
Hmm.
year, and
Hmm.
students go with more subjects,
Hmm.
and they can learn with a more slighter pace, not
Hmm.
very higher pace. Because in
Hmm.
the month span time,
Hmm.
we are learning very faster, so we can miss some topics, and there is some weak links may be left behind, which we can't.
Because of 3 terms, right?
Yeah,
If it is 2 terms, I think it is moderate and equal kind of speed, right?
yeah, and you can learn it properly,
Correct.
because if you are getting 5 to 6 months, if there is 2 semester in a year.
Correct.
And
That-
also the quizzes are also creating some gambling, I can say, because there is each and every quizzes you can't score good marks. You are a human being, you are not a machine. That's
Correct.
the reason that I am facing very difficulties, because somehow before a quiz you got some health issues, your quiz go wrong, and that's affect your CGPA a lot.
Correct. That's one suggestion. Yeah, that's good one. But I don't know why when they were structured itself 2021, they made it is 3 terms. I don't know why it is, because maybe it was online degree
I
or
guess, yeah, people will like if they see right now, if they have to wait for 6 months for an entry, like I'm speaking out of the box.
correct.
That might be the reason. Like actually, I feel this is like a startup. I feel in the starting days. So to increase attraction, at least 3 months should be good for admissions rates.
Correct.
Because 6 months would be too much time. People might move off.
Correct.
That
Immediate
might be the
admissions we
reason.
can grab, right?
Yeah.
Yes, correct. Yeah. Now there should be that some kind of commercial thing also we have to have, right?
Yeah,
sir.
yes, sir.
But
Most is, I am sorry to say, 99% is commercial only.
Correct.
1% is that last year, fourth year guy, IITM is losing on the last side. 99% they're making money.
Correct.
Yeah.
That's
It's a business. It is a business model.
correct. Okay.
We are just consumer.
Correct. Yeah, that's right. Okay.
Thank you, sir. Thank you
Okay,
having
then.
for discussion.
Okay,
Yeah,
then.
fine.